And now recording. All right. I'm actually done with yesterday's stuff. I only needed 1 day for 3.7 and 3.8, so I'm already up to 3.9. Okay, so I might be considered a little bit ahead, but I want to make sure I cover everything so there's enough time to give you a buffer day, a day for questions and answers next Thursday. I hope to finish everything by Wednesday. In fact, even this week, I want to tell you even a little bit about 3.11, a little bit about everything and all the formulas that you need. So rather than just having like 2 days before the test to tell you ahead of time, okay, these are the formulas you need. So you have a week to prepare at least your formula sheet as opposed to just 2 days over here. So I'm hoping to, again, next Thursday, leave it as questions and answers. Then Friday the 26th is a test. And then, of course, we're off for a week for spring break. Okay. All right. So I was done with 3.6 and 3.7. I thought I'd let you know also for Friday's quiz, it'll be material similar to yesterday's stuff. Okay. So exponential growth and decay. Okay. Stuff that we did yesterday. Okay, so we had growth situation like population growth and decay like radioactive decay, half-life, stuff like that. Okay, so quiz on Friday will only be that kind of stuff. Okay, from 3.8 specifically. Right. Okay, so I'm going to start 3.9, which is on related rates. So I'm a little bit ahead of the schedule because I anticipate maybe falling behind, but I want to make sure that I finish everything again in preparation for giving you next Thursday for questions and answers, and then Friday for the exam, as we know. Okay. All right. Okay, so related rates. They're all word problems. Okay, so 3.8, I can mark that off. I think I've given you enough of that. So 3.9, 1 to 13 odd, 17 to 23 odd, 29, 37. So once again, let me show that to you for the benefit of those of you that don't have the book and don't plan on getting it. So 37 is the highest from 3.9. Okay, topic again is related rates, page 245. Okay, so you can see it's pretty much all word problems. So just go quickly. Again, I'm not holding it that long because you can always check the video and pause, rewind, fast forward as much as you wish. So again, I only need to have it focused for a split second. There's that. So all these word problems, of which I'll do several. Okay, so I think that's that. And let's see, how far are we supposed to go again? 37, was it? Okay, so on page 250. 21, 23, 25, 27, 29. Well, 29 starts there and it continues over here. And 31, 33. I don't think you had to do 35. 37, I believe, was the last one. So there we go. Okay, so I think everything is readable. All right, so here we go. Related rates. 3.9. In related rates, we differentiate with respect to t, time. There's time involved in every single one of these problems, hence the term rate. Okay. When you even have the word rate, way back in Algebra 1, when you had an equation such as distance equals rate times time, right? Rate was like miles per hour, feet per second. There was always a time involved. So all these problems involve time. We're differentiating with respect to t, time. Okay. That means when you differentiate here, every variable by the chain rule needs a d variable dt when we differentiate. Now, remember when we were doing implicit differentiation? Okay. when we did implicit differentiation, if I had an x, we just took the normal derivative, but when we had a y, you had to multiply by dy dx. Okay. This time, however, every letter, x and y, and whatever other letters there may be, needs a d variable dt. So that means x needs dx dt, y needs dy dt, and etc. That's the algorithm. Okay. If you want to know on a deeper scale what's happening, it's a variation of the chain rule. Okay, where you have x and y are functions of t. Okay, so if to differentiate with respect to t, okay, it's a chain rule. Sometimes you have to differentiate with respect to x and then times dx dt. And then you differentiate with respect to y, dy dt, and so on. Okay, now by way of example, and again, you can put this on your cheat sheet if you want. Okay, x squared plus y squared equals 1, our famous unit circle. Okay, this can actually be done two different ways depending on whether you're doing implicit differentiation or related rates. So I'm going to show you how they work. Same unit circle, but implicit differentiation we've already seen. Related rates is now different. Okay, so implicit differentiation you already know. X squared plus y squared equals 1. Differentiate both sides with respect to x. So x squared 2x. Y squared plus 2y, and then have to tack on a dy dx because there's a y involved, right? Equals the derivative of 1 is 0. And then I just say, etc. You can algebraically solve for dy dx. That's easy. Subtract 2x, divide 2y, blah, 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 blah. Okay, but that's what's going on now. Related rates. This is different. I start off with the same equation, but now every variable needs a d variable dt. So when we were doing implicit differentiation, it's like x is exempt. Just do the regular derivative, 2x. Not for y. We had to go 2y dy dx. Now every variable needs a d variable dt. Okay, and again, the reason why I prefer you write dy dx here, so at this stage you have to write the d notation, the Leibniz notation, so you're already ready for it. So look at how this goes. 2x dx dt plus 2y dy dt equals 0, and then etc. Solve for whatever they tell you to, solve for dy dt or dx dt, as the case may be. Okay, so the principle again is up here. If you want to put this on your formula sheet, you may. For related rates, every variable needs a d variable dt, no exception. So over here, x was exempted, right? It didn't need any extra d stuff, right? Implicit differentiation, derivative x squared, 2x. Derivative y squared, since there was a y, you have to go 2y times dy dx equals 0. Here, no letters exempt. X squared needs a dx dt, y squared needs a dy dt. Later on, there'll be a z squared, you need a dz dt or whatever. Okay, every letter needs a d letter dt because we're differentiating with respect to t, which stands for time. Okay. What is dx dt? Rate of change of x with respect to time. Rate of change of y with respect to time is dy dt. Okay. Now the context should make it clear, right? So if you start off with this equation or this equation, say, well, how do I know if I'm doing this or this? Okay. If you see any time involved, related rates. Okay. Because there's a dt. So if you see in a problem, rate of change is blah, blah, blah per second, per minute, per hour, per year, per day, then you know it's a related rates. If there's no time involved, then it's probably implicit differentiation, or the directions might go ahead and tell you. Directions will tell you right off the bat whether you're doing this or this. Okay. So now, how do you do these problems? Okay, so let me go ahead and get started. Let me quickly check the chat on some things. Okay, so yeah, some people, if you just, anybody who just joined late, then go ahead and put it in the chat so I can get you for attendance late. Okay, I think some of you just did that. Okay, so how do I take all these words and make it into related rates problem? Okay, so number one, V is the volume of a cube with edge length X, and the cube expands as time passes. Okay, find dV dt in terms of dx dt. Okay, dv dt stands for rate of change of volume with respect to time. Dx dt, rate of change of x with respect to time. And the nice thing about the D notation, the Leibniz notation, L-E-I-B-N-I-Z, is it tells you exactly what the variables are. Volume and time, x and time. Okay, how do you find the volume of a cube? If one side is x, it's x cubed, right? So here's all you do. Volume equals x cubed. Here are my two variables. So I differentiate both of these with respect to time. So V needs to have a dV dt, X needs to have a dx dt. Okay, so what's the derivative of V? 1 times dV dt equals, what's the derivative of x cubed with respect to t, as we say? So 3x squared times dx dt. So that's all there is to it. Okay, so dV dt, dx dt. Right, now, granted, that's only problem 1, and that seemed pretty easy, but don't worry, they get it much harder later on down the line. Okay, so you have to have an equation. Either you are given an equation or you have to come up with the equation. And then every letter, when you differentiate, okay, every variable needs a d variable dt. Okay. All right, 5. A cylindrical tank with radius 5 meters is being filled with water at a rate of 3 meters cubed per minute. How fast is the height of the water increasing? Okay, let's just think about what these are. So what language would I have for this? Rate of change of volume with respect to time. That's dV dt. Rate of change of volume with respect to time. How fast is the height changing? So what am I looking for? dH dt, rate of change of height with respect to time. Okay, and again, if we were meeting face to face, it'd be a lot better. I can show the problem, leave it up here, and then write on the board, but I can't show you both at the same time, unfortunately. So we'll just have to live with it. So I'm going to draw the picture and give you all the important data as we go along. So here's a cylinder. Radius is 5. Here's the height. They tell me the volume is increasing at 3 meters cubed per minute. Okay, that's dV dt. Now you say, well, how do you know it's dV dt? This is volume, meters cubed, right? Square meters is area, right? Cubic meters is volume. And the units for time is minutes. So it's volume over time, so dV dt. All right, so I start with the formula for the volume of a cylinder. Okay, the volume of a cylinder is the cross-sectional area, it's a circle, right? Times the height. And what's the formula for the area of a circle? Pi r squared, right? Cross-sectional area times the height. So the volume is pi r squared h. Okay, formula for the volume. So again, if you have a cylinder like this, you take the cross-sectional base times the height. So cross-sectional area, pi r squared, right? Formula for the area of a circle, pi r squared. Okay, now they tell me that radius is 5. So I just plug in 5. 5 squared is 25. So volume is 25 pi h. Okay. Right. Now I take the derivative of both sides with respect to time. Okay. So again, every variable needs a d variable dt. So in this problem, what are my variables? V and h. Is pi a variable? No, pi is a constant. 3.14159, blah, 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 right? It's a weird constant, but it's a constant. So the coefficient here is 25 pi. 25 times 3.14. So 75, 70 something, right? So what's the derivative of V? 1 dV dt. What's the derivative of 25 pi h? 25 pi. It's like asking what's the derivative of 9h? It's 9, right? 25 pi h, 25 pi times dh dt. Okay, what is dV dt? dV dt was given to be 3. So I plug in 3 over here. Divide both sides by 25 pi. And I have it. So dH dt is 3 over 25 pi. And what are the units? Okay, the easiest way to get the units is what are the units of height? What are the units of time? So height, the volume was in cubic meters. So height is just meters. And the only time given in the problem was minutes. Okay, so 3 over 25 pi meters per minute. Again, ground rules, whenever you have a chance to give the exact answer, do so. So you can leave it like that. You don't have to give a decimal approximation. 3 over 25 pi meters per minute. Although, okay, this problem is now considered finished. But if I were to keep going on, it's roughly 1 over 25, right? Can you see even without a calculator? How can I guess it's 1 over 25? Because what's 3 over pi? 3 divided by 3.14, it's about 1, right? So if I round that off to 1, it's roughly 1 over 25. Not quite. A little bit smaller, I guess. But that's just a way that you can guesstimate in this case. All right, so that's dH dt, the rate of change of the height with respect to time. And units are meters per minute. Okay, so take the given information, come up with an equation. Okay, so here's the volume of a cylinder, cross-sectional area, pi r squared, times the height. They told me r is 5, so I plugged that in. Differentiate with respect to time. So 1 dV dt, 25 pi dH dt, and then solve from there. Okay. All right, next one I'm going to show you was 11. Here's our first instance of having 3 variables. 11, x squared plus y squared plus z squared equals 9. This is 3-dimensional. You'll get that in Calc 3. Okay, and I'll just mention a little bit here. You just kind of go by analogy from 2 dimensions. In 2 dimensions, do you recall what's x squared plus y squared equals 9? It's a circle centered at origin, radius of 3. X squared plus y squared equals 9. So guess what happens here? Sphere, 3 dimensions, x, y, and z, right? This way, and this way, your 3 dimensions. Center at the origin. Of course, for the origin in 3 space, you can't say 0, 0. You'd have to say what? 0, 0, 0, 3 dimensions. Okay. So in Calc 3, you'll be doing a lot of 3-dimensional stuff. This is a sphere. Sphere, center of the origin, radius of 3 in every direction. So 3 up and 3 down and left, right, forward, backward, sideways, that way, that way, that way. You get a sphere. Okay, they give you dx dt, dy dt. Find dz dt when x, y, z is 2, 2, 1. This is an ordered triple, as you might guess, x, y, z. So most of our work right now, we've been doing ordered pairs, right? Up to now, you've done only ordered pairs. In Calc 2, you'll be doing ordered pairs, but once you get to Calc 3, those of you that need Calc 3, you'll be doing ordered triples, x, y, and z, in the x direction, y direction, and the z direction. So imagine a sphere. Here's a point in space, okay, not in the xy plane, but in space, where x is 2, y is 2, z is 1, okay? And you're given these rates of change, okay? What will dz dt be in this case. Okay, so a little bit of foretaste of what it's like to have a three-dimensional calc. All right, so here's our first instance of being in 3 dimensions. X squared plus y squared plus z squared equals 9. It's a sphere. Okay, as you might guess, this is a circle, center of the origin, radius of 3. This is a sphere, center of the origin, radius of 3. So of course, when I have 2D, the center, the origin, we would say 0, 0, right? Once you get to calc 3, those of you going on calc 3, the origin is 0, 0, 0, because you have x, y, and z. And the given point that they give you 2, 2, 1, that's an ordered triple, x, y, and z, not just x and y, right? We're used to x and y, but in calc 3, you have x, y, and z, 2, 2, 1. But in any event. And here's all the important data. dx dt is 5. Rate of change of x with respect to t. How does x change as time goes by? dy dt. How does y change as time goes by? We're looking for dz dt. All right, so look at how we take the derivative here. In related rates, we differentiate with respect to t. Every variable, in this case, x, y, and z, or p, q, r, whatever, every variable needs a d variable dt. Okay, and by the way, you might look back over here, quick timeout for question 5. You say, well, I didn't have to do any dr dt. Yes, because r was a constant, it wasn't changing, right? R is 5, so I can just plug in right away. So it's not considered a variable really. R is a constant, in this case, 5. Now, if they said R was changing also, the radius was increasing or decreasing, I would have to have a dr dt. Not so here, R was constantly 5, so I can just plug in right away. So I had no need for dr dt. The volume's changing. In fact, they told us the water was increasing, right? So if the water increases, the height obviously increases, so there has to be a dh dt. The radius was not changing, so there didn't need to be a dr dt. But here, all 3 of these letters need a d letter dt. So look at how it goes. It's all pretty much the same. 2x dx dt plus 2y dy dt plus 2z dz dt equals the derivative of the right side. That's easy, that's 0. Okay, so please notice again, doesn't matter how many letters you have, every letter gets a d letter dt. So x needs a dx dt, y needs a dy dt, z needs a dz dt. Okay, so derivative of x squared with respect to t, 2x dx dt. Derivative with respect to y, 2y dy dt. Derivative with respect to z, 2z dz dt. Okay, now look at what happens. I know x, y, and z because they told me it was 2, 2, 1, right? So 2 goes there, 2 goes there, 1 goes there. I know both of these guys. dx dt they told me was, where'd it go? 5. dy dt told me was 4. Plug everything in and then algebraically solve for dy dt. Okay. Yes, optionally you could solve for dz dt first. Yeah, I think if they give you the numbers, you might as well plug it in. I mean, it's a lot easier to use numbers and letters, right? Okay, so here we go. X is 2. Oh, by the way, I divided both sides by 2 to get rid of the 2, right? Alternatively, you can say factor out a 2. 2 parentheses, x dx dt plus y dy dt plus z dz dt equals 0, and then divide both sides by 2. Okay, so I lost the 2, 2, 2. You can do that, right? All right, plug in x. X is 2. Y is 2. Z is 1. Plug those in. dx dt was given to be 5. That goes there. dy dt was given to be 4. That goes there. Again, I lose the 2's. Divide both sides by 2. Or you can say factor out a 2 and then divide by 2. Okay, so I have 2 times 5 plus 2 times 4 plus 1 times dz dt, just dz dt. And now it's just simple algebra. So that's 10 plus 8 plus dz dt equals 0. 18 plus dz dt is 0. So dz dt is negative 18. And there we go. Okay, so again, every letter needs a D letter dt. X, Y, Z. If you have another letter, put that also. Well, we've seen all kinds of letters. V for volume, H for height, right? X for side length. So all of these are possible. All right, so that's that one. $13. Okay, now you don't have to specifically do A, B, C, D, and E, just as long as you get the answer. You are going to need to draw a picture, though. You can't really tell what's going to happen unless you draw a picture. So we will come up with a picture. Okay, 13. So move this over here. A plane flying horizontally, so it's not going up, not going down, at an altitude of 1 mile, speed of 500 miles an hour, passes directly over a radar station. Okay, you can imagine the plane flying overhead. It's level, it's not going up, it's not going down. It says it's a mile up. Okay, and there's a radar station, it passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. Okay, so I drew myself a little picture here so you can see what's going on. Okay, so here's my little picture of the situation. Plane is flying horizontally. It's not going up, not going down, 500 miles an hour. 1 mile up. Okay, so let's say it's going this way. Okay, so I'll call this X, I'll call this Y, this is 1. Okay, so as the plane is moving this way, the distance that the plane is moving away from the station is increasing, right? As it goes like that, the distance goes like that. So if I over here, right, it's like that, the hypotenuse keeps changing. So what's the rate of change of the distance away from the station when it is 2 miles away? Interpretation, find dy dt in my picture. Okay, here's 1 mile, X, which moves, Y moves, the 1 does not move. Okay, from the words, it's flying horizontally, doesn't go up, doesn't go down, so its distance above the ground stays at 1. So I decided to call this X, I decided to call that Y. Find dy dt. Show you the words again. So 13, find the rate at which the distance from the plane to the station, that's what I called Y, is increasing, dy dt, when it is 2 miles away from the station. Okay. I have a Pythagorean relation. X squared plus 1 squared equals Y squared. Pythagorean theorem, right? Hypotenuse is Y, X squared plus 1 squared equals Y squared, or X squared plus 1 equals Y squared. Right? That means I can solve for X. Okay, so they tell me I want to know what happens when Y is 2. Put a 2 right here. X squared plus 1 equals 2 squared, which is 4. So X squared is 4 minus 1 or 3. X is radical 3. Okay, so this distance is radical 3. It's about 1.7. All right, I have my equation. So now I'm ready to do my related rates equation. Differentiate this with respect to t time. So every letter gets a d letter dt. So what's the derivative of x squared? 2x dx dt. Plus derivative of 1 is 0 equals the derivative of y squared, 2y dy dt. I'm trying to find dy dt. So I divide both sides by 2y. So divide by 2y. I have 2x divided by 2y. 2 cancels out. So dy dt is x over y dx dt. Divide both sides by 2y. Now it's just a plug-in. Okay, can treat dy dt as one symbol, dx dt as one symbol. So in other words, don't try to divide this out or put something on top and not on the bottom. No, dx dt is one symbol. Pretend it's a new letter of the alphabet, and this is the way you write it. This is a brand new letter of the alphabet. So don't split it up. Don't cancel the d's or anything like that. That whole thing is one symbol. Rate of change of y with respect to time. Rate of change of x with respect to time. Okay, now I just plug stuff in. So x I found to be radical 3. Y was 2. dx dt, rate of change of x with respect to time, that was 500 miles an hour. They told us that, right? How is x changing as time goes by? 500 miles an hour. All right, so radical 3 over 2 times 500. 500 divided by 2 is 250. So exact answer is 250 radical 3 miles per hour. But this is an example where you definitely should give an approximation. So 433 miles per hour. Okay, so you should give me this. But I mean, just think common sense, real life. You don't talk this way, right? Like nobody says, how fast are you traveling? Well, I'm traveling 250 radical 3 miles per hour. Nobody says that, right? So you would give an approximation, 433 miles per hour. So the answer is 433 miles per hour. Now, what is that 433 miles an hour? Okay. The plane is moving 500 miles an hour. The rate of change that the plane is moving away from the radar station. Okay. So over here, it's going to be like that. And over here, it's like that. That rate of change is 433 miles per hour right at that instant. Okay. Okay, that might be necessary. Like maybe these are control towers, right? So as the plane is flying by, you want to be able to contact the control tower. And maybe after a certain amount of time, you can't reach the control tower. So you have to, go to the next control tower for the destination you're heading to, right? Okay, so if you're flying, let's say to Los Angeles, after a while, you can't hear what's going on at SFO. And so, after a while, you might be out of range. So, okay, I'll pick up the Los Angeles tower now. And so at my rate of speed, you can figure out, okay, after a while, I'll be out of range. I can't hear SFO, San Francisco Airport anymore. And then maybe I want to start communicating with the Los Angeles people or whatever. Okay. So that's what this represents over here. All right, let's see, it's about 9:45. I'll set up one more, and then I was going to stop and let you try to do one in class. Okay, so, but I may not be able to finish this one. Okay, so maybe I'll just set you up for this one and then finish it next time. Okay. Or maybe not finish it and let you try to finish it. Okay, 17. Two cars start moving from the same point. One travels south at 60 miles an hour. The other travels west at 25 miles an hour. At what rate is the distance between the cars increasing 2 hours later? Okay, so again, I can't show you both at the same time, but here's the important data. All right, so two cars start together. One's going west, 25 miles an hour. I'll call that X. This one's going south, 60 miles an hour. Call it Y. And I decided to call that Z. There's a very obvious Pythagorean relation. X squared plus Y squared equals Z squared. Okay, now it says after 2 hours. Okay, what I have in red are the distances. Okay. If I drive 25 miles an hour for 2 hours, it said 2 hours, right? 25 miles an hour for 2 hours, X is 50 miles, right? If I drive 60 miles an hour for 2 hours, I've gone 120 miles. I can use my a squared plus b squared equals c squared to find the hypotenuse. You can take my word for it, or maybe you know that triangle, it's 130. Okay, maybe in trig, did you ever memorize the 5, 12, 13 triangle? You've probably heard of 3, 4, 5. You did a lot of 3, 4, 5 right triangles. 5, 12, 13 is also a right triangle. In other words, 5 squared plus 12 squared equals 13 squared, but you can have any multiple of that also. It's like 50, 120, 130, or 5 million, 12 million, 13 million. It's still a 5, 12, 13 triangle, right? But you can take my word for it. 50 squared plus 120 squared is equal to 130 squared. It's a 5, 12, 13 triangle. Okay, so here's the setup. So please notice this principle over here. Every variable needs a d variable dt. So we've already sort of done this. So what's the derivative of x squared? 2x dx dt plus derivative of y squared, 2y dy dt equals 2z dz dt. What are we looking for? dz dt. How do I know that? It says rate of change that the cars are moving away from each other. See if I can show you that. For 17, at what rate is the distance between the cars increasing? Rate of change of the distance between the cars. Distance between the cars is z. So as one car goes this way and the other goes this way, right? They're moving apart at a certain rate. What is that rate of change? That's dz dt. Now you basically just plug everything in. Oh yeah, you could cancel the 2's like in the previous problem, or you can just plug everything in. So x, y, and z, I plug in 50, 120, and 130, right? So 50 goes here, 120 goes here, 130 goes here. dx dt, 25. dy dt, 60. And then algebraically solve for dz dt. Okay, and what are my units going to be? Z is miles, time is hour, so it's miles per hour. So just plug everything in, and that's it. Okay, actually, I've done the majority of the problem. Now you just clean up the algebra. So I don't really have to show you this tomorrow or whenever, right? Just multiply that. 2 times 50 times 25, 2 times 120 times 160 equals 130 dz dt. So work this out and divide by 130, and that's pretty much about it. Okay, so I was going to stop today, folks. Let me show you a little bit more of this, doing my focusing thing again, in case you couldn't read it. You can always watch the video later. And that. And that. And that. And yeah, hopefully that's good enough. Okay. All right. So I'm going to have you do one problem now in class on page 249. It's an even problem number 2. Okay. And I just want 2A. Okay. And if you have absolutely no idea what to do, look at what we did for number 1. It's the same kind of thing. Okay. So 2A, please. I'll hold it up for another 30 seconds or so. A is the area of a circle with radius r, and a circle expands as time passes. Find dA dt in terms of dr dt. Okay. We know the formula for the area of a circle is pi r squared. Okay. Now you're going to have to write pi in your chat. Just type pi. Okay. Rather than trying to find a Greek symbol. So for pi, just type pi. So area is pi r squared. Okay. So answer 2A. If you have no idea what to do, look at what we did for number 1. It works in a similar fashion. You should be able to type dA dt. You should be able to type dr dt. And again, for pi, just type pi. Okay. And when you type it in, you can leave, and I'll see you tomorrow. Okay. So I will assume everybody has it now. 2A on page 249. The formula is area is pi r squared. Okay. So differentiate there. dA dt is blah, 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 dr dt. Okay. So that's it. And I'll see you tomorrow. I will stop the share and stop recording also.